Hey guys, in this video we're going to go ahead and graph some transformations of a quadratic function that is in vertex form. Now, when we graph these functions, before I even get into this, where you already see stuff going on in these problems, let me go ahead and let me go ahead and show you what a regular quadratic function is going to look like. A regular quadratic function in vertex form is going to be f of x is equal to, a times x minus h squared plus some k value, like that. Now, why do we write it like this? Well, if it's in this form right here, it is very easy to graph, extremely easy. And so it's very handy, all right? Kind of like standard form and slope-intercept form for lines. Each of those has a perfect place for problem solving. So do quadratics. They have two forms also. In this form, the vertex can be found at h comma k. But look at that right there. As with absolute value functions, we have a negative in the formula, which means you're going to have to, whatever your h is in the parentheses here, you have to take the opposite of it, just like you did for the vertex for an absolute value function. The k value, just like in absolute value functions, is going to be as is. We're not going to change that at all, okay? So that's what it's going to look like, and here's what the graph normally looks like. So the graph of a parabola or quadratic function, let's go ahead and look at this. Let's look at f of x is equal to x squared. That's the most basic one. That's what we call the parent function, because all the other quadratics are going to be based upon this. They're just going to be transformations, just like absolute value was. So as we remember from class, you're going to go from the origin right there, and you're going to go over 1, up 1. And why is that? Because 1 squared is 1. All of these are based on some kind of a squaring process. So that squaring process is going to determine where my y values are. And it's very easy if you graph it this way. My next point would be over 2 up, not 2, because it's not absolute value, over 2 up. Well, what's 2 squared? 4. 1, 2, 3, 4. And that's how we're going to get that nice parabola, that nice curve that goes up like this, okay? I'm not sure if I can show the next one up here, but if you went over 3, you can go up 9 units, but I can't really fit that onto the screen here. All right, on the other side, you can go ahead and put your points on the other side, because like absolute value, this line right here, this vertical line, is like a mirror, and we call that the axis of symmetry. All right, so on the right side and the left side are identical for all of these parabolas. Okay, normally then you would go ahead and just connect your dots smoothly, as smooth as you can. Nobody expects perfection, but the more times you do it, the better you get. And then there's your graph, and that was just y equals x squared. Okay, so very simple. There's your parent function. Now let's move on to some transformations. So the first one we have here is x squared plus 1. All right, so what that's going to do is it's going to take your parent function and it's going to slide it up 1 unit, push it up 1 unit. So the vertex used to be here, now it's going to be here. Now, since there's a 1 in front of the x squared, it's business as usual. Over 1 up 1, over 2 up, 1, 2, 3, 4, and then that's it. On the other side, over 1 up 1, over 2 up 4, and then that's all we can fit on there because the graph is kind of small, and then we just smoothly connect our points. And that's a good looking parabola right there. If you talk about the domain and range, the domain of this function here, from left to right, you go from arrow to arrow with no breaks in here at all, no jumps, no pieces of it that are missing. And so from here to here is going to be all real numbers, because this part and this part keep going up and over a little by little by little to infinity. So for your domain, okay, so that's going to be all real numbers. For your range, that's different. For your range, it's going to start at 1, and it's going to go up with no breaks, no pieces missing, all the way up to arrows. So that means from my range, that's going to be all y, and this would be greater than or equal to whatever that value for y is, and that's a 1. And you can put that in set builder notation if you want to. All right, so that one's done. So let's look at this one over here. And I think this one's actually in order. Okay, so here we have x squared minus 3. All right, not much different. Instead of going up 1 in the last one, we're going to just go down 3 this time from the origin. So 1, 2, 3, we'll put a dot. All right, let's see how this works. It's got a 1 up here. So over 1 up 1, over 2 up, 1, 2, 3, 4. Over 3 up, what's 3 squared? 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, and we can sneak that one onto the graph right there. Now, the great thing about quadratic functions is if you know where the vertex is, the other side is going to be identical. It's just going to be going in the opposite direction. So over 1 up 1, and you can even just do this, which I do a lot, just to save some time. Again, if you're unsure of any of those points, you can always plug the x and y values back in and make sure you get a true statement, which means it's a solution of the function and it belongs on that curve. So now I'm going to smoothly connect these dots. I always call them dots. I should call them points. And that's pretty good. Okay, let's talk about the domain and range. For this one, the domain is going to be, again, you go from arrow to arrow with no missing pieces in there. So it's just going to be all real numbers. And every one of these in Algebra 1 is going to be all real numbers for your parabolas, every one of them. In other classes where they're going like this to the side, we call those conic sections, then it's going to be different. But for all of ours, your domain is all real numbers. But what about the range? Because the range is not going to be all real numbers. So this time, your y values begin at -3. They go up until you hit the arrows. So from -3 on up in the positive direction for y, it's going to be all y greater than or equal to -3. All right. Now let's look at some other ones here. Okay, this one, x minus 2 squared. If you remember from absolute value transformations, that -2 is going to slide it not to the left, but 2 to the right. It didn't go up or down. You have a 1 in front, so that means you're going to go over 1 up 1, over 2 up 1, 2, 3, 4, and that looks like that's it. We can't fit any more on there. Back 1 up 1, back 2 up 4. We see the pattern just like it should be. Connect our dots. And there it is. So for the domain, all reals. Range. Okay, the range here, again, bottom to top. It looks like the vertex starts at 0 and it goes up until you hit arrows. So from 0 on up would be all y greater than or equal to 0. All right. On this one, we have x plus 3 squared. Okay, so what's going to happen here? Plus 3 means 3 units, not this way, this way. Back. There's our new vertex. We got a 1 in front, so over 1 up 1, over 2 up 1, 2, 3, 4. Back 1 up 1, back 2 up 4. Connect the dots. And there's our graph. Let's look at the domain and range. From this one to this one. Did it really change it all up or down? Not really. The vertex is still at 0 there and it's still at 0 there, right? Your domains are going to be the same. And for this one, even though it's been slid over to the right, your ranges are going to be the exact same number because it starts at 0 and goes up again just like the last one. So for this one, your domain again, all reals, your range, y greater than or equal to 0. All right. Now, let's take a look at some that are slightly more complicated. Let's look at this one. Now, we are not going to discuss domain and range here for this one, for these, which is okay. This is just practice graphing. Just like absolute value, we got a +1, which pushes it back 1. A -1 pushes it down 1. And when I say it, I'm referring to the vertex. So the vertex is going to be back 1 and then down 1. Back 1, down 1 right there. You have a 1 in front. So over 1 up 1, over 2 up 1, 2, 3, 4. Same thing on the other side. Okay. We're going to go ahead and connect our points. Okay, and there's our graph. The axis of symmetry is right here at x equals -1. And so there's your mirror right there. If we look at this one's going to push it forward 1 unit and then push it up 2. So forward 1, up 2. There's your vertex. Okay, we're going to go over 1 up 1. Over 2 up 1, 2, 3, 4. And we've hit the top there. Same thing on the other side. Okay, connect our dots, points. That was the best one I've ever done, but it'll work, and that looks good. All right, next example. Here we have x plus 2 squared minus 3. All right, this one is going to be back 2, left 2, down 3. Back 2, 1, 2, 3. There's our vertex. All right, again, a 1 in front, so over 1 up 1. Over 2 up, 1, 2, 3, 4. Over 3 up, 1, 2, 3. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up at the top. Axis of symmetry is right here. It's x equals -2. Go back 1 up 1. Back 2 up 4. And the next one's going to be right there. And you can tell right away if your graph is going to look good because all the points look like the shape it's supposed to be. Okay, so now I'm going to connect my points. And on the other side. And there's my graph. Number 8, this one right here. -4 means we're going to go ahead 4 units, right 4, and then up 1. So 1, 2, 3, 4, up 1. There's a new vertex. Again, we have a 1 in front. So over 1 up 1. Over 2 up 1, 2, 3, 4. Can't get any more. Axis of symmetry is right here. That's x equals 4. Back 1 up 1. Back 2 up 4. There's your shape. Just like all the others. Connect the dots. Okay. Now, let's move on to a couple that are a little more interesting. Let's look at this one, -3x squared. Okay, this one has no left or right, no up or down, only this -3 right there. So how do we deal with that -3? Well, our vertex is going to be at the origin because it did not go up, down, left, or right. It's stuck right there. This -3, if you remember, controls how wide or narrow it gets. All of your y values are going to be multiplied by 3, actually -3. And so what's going to happen is, instead of going over 1 up 1, you're going to go over 1 up 1 times 3. 1, 2, 3. However, you have a minus there. So we're actually going to flip it down, because that's a reflection across the x-axis. Over 1 down 3. And if we went over 2, we would normally go over 2 down 4. However, 4 times 3 is 12. And that's what's going to make it real narrow. So we can't really fit 12 on here. And so we just kind of have to be satisfied with these two for the meantime. Over here, our axis of symmetry is right there. So we're going to have that point, and that's really all we can fit on there. And so we just kind of do the best we can, and that is that. Okay. The next one I really meant for one of these to be positive and one to be negative. So what I'm going to do is I'm going to make that a positive 0.4 instead of 0.4. Okay. So just kind of ignore that wasn't negative. So we're going to graph 0.4x squared. Okay. Let's take a breath because we see a decimal there and we know that that's going to be a problem. So here we go. Did it go left or right? No. There's no parentheses. There's no plus or minus in parentheses. Did it go up or down? No. The constant is just a 0. That's why you don't see it. So we can conclude that our vertex is going to be at the origin. Okay, so here comes the fun part. We're going to have to figure out where our dots are going to go. All right, remember, all of our y values are going to be immediately multiplied by 0.4. And what that's going to do is it's going to make it narrower, because any number here between 0 and 1 is going to be widened. It's going to be a widened graph. This one was narrower because you have a number bigger than 1. This one is going to be wider. Sorry, I misspoke there. So how are we going to do that? Well, it used to be over 1, and we're making it positive, over 1 up 1, right? However, it's now going to be over 1 up 1 times 0.4. Well, that's easy. That's just 0.4. So what we have to do is kind of guesstimate where 0.4 is. And it's a little bit below halfway. And it's okay if you're off by a little bit. Everybody usually is. All right. I'm going to go ahead and immediately graph that other one over here on this side, because I don't want to have to do all of this twice. Now, what about the second one? It used to be over 2 up, 4, right? Now it's a 0.4 multiplier sitting there. So now what I have to do is I have to do 0.4 times the 4 that it used to be, and I get 1.6. Okay, so it's going to be over 2 up 1.6, which is a little bit higher than halfway. I'm going to go ahead and put the other one on the other side. And we can already see this widening out, right? All right, it used to be over 3 up 9, right? But now we have the 0.4 multiplier. So what is 0.4 times 9? And that gives me 3.6. So I'm going to go over 3 up, 1, 2, 3, and then a little bit over halfway right there. And I'll put the other one on the other side right there. All right, let's see if we can get one more. It used to be over 4 up. Well, what's 4 times 4? 4 squared. 16, right? It used to be over 4 up 16. That's a lot. We're multiplying that 16, though, by 0.4 to make it wider. So let's do that. So 0.4 times 16 is 6.4. That's a little bit off the graph, but you know what? I think I'm going to sneak that on in. Over 4 up 6, and then 0.4 would be just a little bit more right there. If I sneak that one in, it's going to make it easier for me to sketch this curve. Okay, so we do see that it got wider, didn't it? Like this one was just a 1 in front of the parentheses. This one is a 0.4, so it did get wider. We're going to go ahead, and you always want to make this go out a little bit, curve up. You never want to make it go straight up, okay, ever, because then that wouldn't even be a function. So this part over here, we'll sketch that on there, and we are good to go. That's a good looking graph. So guys, I hope this helps, graphing some quadratic functions in vertex form. And until next time, make sure to like and share, and we will see you guys later. I miss you guys. We'll see you.